This is Computer Programming 1 from the University of Washington. I'm Martin Dickey. Welcome back. Today in Lecture 5 we'll be talking about input and output. This may seem like a review to you because in previous lectures we've already seen almost everything that I'm going to show you today in a more formal way. We'll talk about doing output with printf, we'll talk about doing input with scanf, and the basic format codes that are used in both of them. Then, as a little bonus topic at the end of today's lecture, I'll talk about initializing variables in a new way. You may have noticed that I'm not wearing a tie today. Well, it's Friday where I am, so I've taken the liberty of being a little more casual. If it's Friday where you are, let me say that you are also excused from wearing a tie while watching this lecture. In the examples we've seen so far, the algorithms haven't been very useful unless we had a way to get data into the program and to get data back out of them. To do that, we used some mysterious things called printf and scanf, and today I'm going to explain exactly what those things are and some of the things we can do with them. Even in our Fahrenheit to Celsius program, although we had a perfectly good algorithm, it wasn't a useful program until I had a way of specifying what the temperature was going to be and what the result would be. In order to give some context to this, let's step back again and look at a by now familiar picture of what a computer is. We've focused so far on the heart of the computer, the central processing unit and the memory. The central processing unit executes instructions one at a time. The main memory holds variables, which are pieces of data that the processor uses as it executes. In contrast to our emphasis on those two components, today I'm going to focus on the rest of the picture. Everything outside the yellow box is generically referred to as the input-output system, or the I/O. This includes an enormous variety of very different types of devices. Monitors, screens, graphic tablets, keyboards, mice, loudspeakers, microphones, the network, the phone line, anything which you might connect to your computer. All of these input and output components have something in common. They are trying to take data out of the memory, or they're trying to put data into the memory. This means we have two essential concepts involved. The first is input, which is the movement of data into the memory from the outside world, from the keyboard, from a joystick, from a mouse, from a microphone. Now, as we take the data from the outside and put it into memory, we are changing the contents of memory. We're referring to memory through variables in C, and so this tells us that input is causing a change in the variables in our program. Sometimes in computer science we refer to such operations as reading data from an input-output device. The complementary operation is output, moving data from memory to the outside world, to a monitor or screen, to a loudspeaker, to the network, to a disk drive. This is often referred to as a write operation. Write operations generally do not change the value of memory. They leave it as it was. Here is text output as it would have appeared from our Fahrenheit to Celsius program. By the way, I hope you've had a chance now to run this program for yourself, both to get familiar with the development environment and to see what sort of things can happen when you actually sit down to type in and run a program. This is text output because all the data is characters, although it's really impossible to see at this resolution. There are some lines of characters that came from the screen, and I'll show you the code in a minute just as a refresher. And there's also a number on the screen that represents the data that the user typed in. So these are keystrokes input from the keyboard. Here are those lines from that familiar program. There was a printf, a scanf, there was an assignment statement with an expression, followed by another printf. Our focus today will be on the details of the printf and the scanf, so that after today's lecture you'll be able to write such statements yourself with confidence in programs that you want to implement. Both printf and scanf have a somewhat similar format. Now, both of them are functions, a topic that we'll get into more details on later. But essentially, a function is a collection of statements or code somewhere else that you can call upon to execute. When the function is finished, it returns control to your own part of the program. Printf is the name of one of these functions. When you go to the printf function, it gets from your program some information. And you show this information within parentheses in the statement. The first piece of information is in double quotes. We can call it the control string. This will give the format of the output and also perhaps some of the text of the output message which you would like to have displayed. Following that, you can have a list of expressions. Maybe none, there may be one, there may be many of them. These represent the variables or expressions which you wish to appear on the screen. You see that scanf has a similar format. It begins with a control string that describes the data you're going to write into, and is followed by a list, in this case a list of variables. You might think there's a typo there, a list of ampersand variables. Well, it's not a typo. That's a special character which will have to be present when you write the scanf, or things will not work right. I'll get back to that later. But that scanf has to be there, or terrible, terrible things will happen. Let's focus on printf first, and we can see most of what we need to know about printf from looking at a couple of examples. In the first one, I have a variable num pushups that I initialize to 5, and the printf statement has a control string saying hello, do %d pushups \n. Then in its expression list, the variable name num pushups. What will happen when this function executes is that what's in the control string will be displayed on the screen, just as you present it in the control string, with a couple of important exceptions. One of those exceptions is that %d. That %d stands for something else. It's a placeholder. What it's holding the place of is an expression from the expression list. Well, in this case, there's only one thing in the expression list, and that's this variable num pushups. So when the printf executes, the %d is replaced by the value of the variable num pushups. So what you see on the screen is do 5 pushups. You don't see %d pushups. You see 5 pushups instead. Okay. There are several different types of placeholders. We'll see a couple of them as we go along. Briefly, the %d means the type of the data that's going to be displayed. Now, a rational person would come to the conclusion that D should be type double. Guess what? It's not. In a totally irrational seeming move, the designers of C chose D to mean integer. And that's the right choice for this example, because num pushups is declared as an integer. So the placeholder needs to be an integer. Maybe you remember at the end of last lecture I said there are many places in C where types have to correspond or match up. This is one of those places where the type indicated in a placeholder, %d or integer, has to correspond to the type of variable in the expression list. There's one other mystery in this slide, and that's that \n. It's not really that mysterious. It's simply a character represented in a special way. This \n stands for the character which causes the screen to start a new line. We call this the new line character. what happens when the new line is sent to the screen is that instead of continuing output at the point where the cursor happens to be, the cursor returns to the next line on the screen and subsequent output will continue from there. Let's illustrate this by expanding the program a little bit to show some printfs before and after the original printf. The first one, hello, there's nothing in the expression list and there's no placeholder. So what appears on the screen is flat out hello, just as it appears in the control string. Now there's no \n in that printf. And so the next time any I/O is done, in fact, I don't even need to say I/O, I can simply say output is done, it will start where we left off last time. So the do 5 push-ups will start right after the hello. Okay. Now at the end of the do 5 push-ups is a \n or a line feed character. This now causes the screen to start on a new line, and so the next printout, do them now, starts there. And you can see the result there will be 2 lines from these 3 printfs. And in fact, if I were to add an additional printf, where would that output start? Would it be on the same line as do them now or not? And the answer is not, because do them now is also terminated with a new line, which will have caused the screen to go to the next line. Now we can get a little fancier with this because the list of expressions could be nothing, could be one item, it could be many things. I have an example at the bottom where we have 3 things in the expression list. Okay, let's find them there in the statement. One is the variable multiplier, the second is the variable pi, and the third is this expression where I've done a cast and a multiplication operation. So you see this lecture builds on what we learned last time about using cast to control your output, to control the evaluation of the expressions. Now here's a basic rule about these list of expressions. For every expression that you want to appear in the output, you have to have a placeholder in the input. Okay. So for multiplier, that's the first thing in the output, and therefore it corresponds to the first placeholder, the %d. The second placeholder corresponds to the second output expression, and the third placeholder, %f, corresponds to the third expression. Oh, wait a minute. What is the %f? We haven't seen that before. Okay, well, the third expression is of type double. Remember, types are really important and you need to be aware of what they are. The type of the placeholder needs to match the type of the expression. And so we have to use a placeholder that corresponds to double. I've already said that contrary to any rational expectation, %d doesn't stand for double, it stands for integer. What stands for double? %f. Okay. That's not totally weird because f also suggests floating point, which is another numeric format similar to double. Okay. As this statement executes, printf will take each placeholder in turn, match it up with the proper expression, compute that expression using what we know about how expressions are evaluated, and then insert that result onto the screen. Okay? So %d is an integer. That will cause the system, cause the printf function to take the variable multiplier, look into memory to see what that is. Now, because of the %d, printf will interpret that as an integer, and it will convert that into the proper symbols for an integer on the screen. A similar thing will happen with pi. That's a %f. And with this expression, double multiplier times pi, that's also %f. So in the final result, what do we see here? we don't see a %d and we don't see the word multiplier. What we see is the value 2 which that expression had. Okay, if you understand this example, you understand just about everything you need to know about using printf. It is really quite straightforward, and a little experimentation when you write your programs will go a long way. Now you can do more than simply let the printf decide how to format the output. You may wish to control things like how many decimal points there are for a floating point value. Do you want it to be a 3.1 or a 3.1000? Maybe if you're doing an engineering or a scientific calculation, you would like the answer to come out in exponential notation. Maybe you'd like to control the total width of the data or field that's printed. How do you do that? Well, I could tell you, and in fact I will tell you some of the ways, but there is such a bewildering variety of options that the best answer is to know some simple ones and know where to look for the rest. Get familiar with your textbook or your reference manual where these topics are discussed. Then if you need an advanced formatting option, you'll be able to look it up. Here are a few. I'll go over just a couple of them to give you a flavor. Let's suppose that you are going to display a double and you want it to occupy exactly 10 positions. This is often helpful if you want numbers to line up in columns, and the numbers themselves might be of different lengths. So you want the column to be exactly 10 positions wide. You want to show exactly 2 decimal places. The placeholder you would use for that is %10.2f. This will give you what you want. If you wanted to show exactly 4 decimal places within a field of width 10, you would say %10.4f. Okay. And I invite you to look at these other examples yourself. If they don't make perfect sense, this is a good opportunity to practice finding the answers in the book and seeing what these fields mean, and then thinking about how you might use those in programs of your own. Let's turn to scanf now. Scanf in many ways is the reverse of printf. Unfortunately, the programming does not always look exactly the reverse. Scanf has a control string, and instead of a list of outputs expressions, it has a list of input variables. Remember that input is a process of moving data into memory, which means changing the values of variables. We have to tell scanf which variables we're changing. And we have to precede the name of each variable with an ampersand. Okay? Later in the course, I'll explain to you all about what this ampersand is for, and maybe even when you can omit it. But for now, you can't omit it. You will have to have it there. This is very important. Let's look at the example. Here we have printfs and scanf mixed. First printf will put out a message. The second one, the scanf, rather, says take an integer field. That's what the %d means. It's integer for scanf as well as for printf. And read data from the keyboard. Place it into the variable named num pushups. Okay? So, when scanf is executing, it will go to the keyboard. It will read the characters that are being typed, and after an enter has been pressed, it will take all the characters it has and it will convert them into the proper bit format necessary for the type of the data. Remember that the bit patterns depend upon the type, so the conversion it does of the characters to an integer may be different from the conversion it does of the characters to a double. That's why types are important. Another example of where it's necessary to know what the types is and be aware of that during the programming. Okay? So the result of these 3 lines of code will then be the block shown in the light blue output. Hello, how many push-ups? The user types in 5. That's a keystroke, a symbol, sent into the system. Scanf picks it up. Because it's %d, it will convert it to the bit pattern for 5. It will store that in the variable num pushups. Now when the printf comes along and sees the do %d push-ups, printf will go to the variable in its expression list, which happens to be the same as in the scanf, num push-ups, get that value out and convert it into a character to send to the screen. And that character is a 5. Okay. It's very important to have that ampersand on the scanf. And it's so important, I'll say it twice or 3 times. What if you don't have it? If you forget it, the program will compile. But when you execute, right, not a nice way to end your day. So please, do me a favor. Do yourself a favor and don't forget the ampersand. One of these days, I will explain it in full detail with you. 1 or 2 more details about scanf that come up in practical program. Involves a notion of white space. This is just a generic term for characters like space, tab, and new lines, which don't show up, don't do any printing on the screen, but occupy some space. Now, when the user types in a number, if there's white space in front of it, scanf ignores the white space. So if you ask the user to enter a number and they type in 17, it's just the same as if they typed in 2 spaces in 17, or a line feed in a 17, or a tab and 6 spaces in a line feed and then the 17. All of that white space is ignored by scanf for integers and doubles. But it's not ignored for characters. So if you want scanf to read in a single character, then you need to remember that the white space is not skipped. Actually, getting scanf to work right with multiple inputs that mix characters and numbers can often be a little bit tricky. Practice is what will help you get that right. Scanf, like printf, can process multiple things in a single call to scanf. And as with printf, and as with many, many things in C, the rule is one of matching. Matching the number of things and matching the types. Let's look at this last statement. Scanf, my control string has 2 placeholders. And so there had better be 2 variables. And there are in this case, so far so good. But that's not enough matching to be correct. There also has to be correct matching between the types. Now let's check that. Okay, the first placeholder is %d, and the first variable is student ID. Great, that matches perfectly. They're both integers. Now the second placeholder is %lf. Actually, the previous slide had %lf too, and I didn't point it out. Why in the world is it %lf? This is another irrational fact. I'm sorry, you'll just have to remember. I can't do anything about it, but here's the rule. For scanf, the placeholder for doubles is %lf. It's not %f, and it's certainly not %d. Okay, so %lf suggests to scanf that the data is going to be a double. And is it? We'll look at grade. Sure enough, grade is a double. So this is all fine. Everything matches up, and scanf will be able to process this just fine. LF is one of several of these little unexpected and perhaps unpleasant surprises. The full table for scanf and printf for our 3 basic types is shown here. If we want to read in a character, it's %c. To display a single character is %c as well. Now here are the ones that are a little hard to remember. To scan in an integer is %d. To print an integer is %d. To scan in a double %lf. To print a double %f. Now in later years, C has been revised so that for integer input you can also use %i. That's what I use myself. I think it makes much better sense. It's easier for someone to read when they're looking at the program. The only reason I don't have it on the slide this way is that the textbook we're following uses %D. And so for consistency, I have %D on all the slides in this course. But you can also use %I as well. You might wonder what happens if the types don't match. And the shorter answer is that it's not good. It's not a good thing when the types don't match. If it's printf and you have the wrong type for the placeholder, it's, the output will look a mess. It just will look totally wrong, but it probably won't do any damage. For scanf, the situation is much more serious. Remember that scanf involves changing an actual memory location. If you have the wrong type specified, scanf may not only get the wrong bit patterns, but it may also, in some cases, change the wrong memory locations, which is a very dangerous and very unfortunate thing. This is not a syntax error. The compiler can't catch this. And even at runtime, the scanf may appear to work correctly, but the program later on during its execution may encounter severe clear air turbulence for an unexplained reason. On older systems like DOS, such errors could actually crash the system, and they still could crash the program that you're running. All right, let's summarize this. No surprises here. Output, as far as we know so far in C, is done with printf that requires a control string and an output list. Input is done with scanf that requires a control string and a list of variables, each of which, for now anyway, must have an ampersand in front of it. And in both of them, it's quite important that the type of the placeholder match the declared type of the variable or the expression. Okay, this brings us almost to the close of today's lecture. Although I have one further topic beyond I/O, let me just pause here to summarize what we've discussed for I/O. Input is the movement of data into memory. Output is the movement of data from memory. And in C, we do this with scanf and printf. It's very useful to know the basic printf and scanf rules and to know them extremely well. However, for the more advanced formatting features of printf, it's only important to know that they exist and know where to look to know how to do them. Look in a reference manual or to some program that you're already familiar with. Well, this being Casual Friday, I thought I would give you a little bonus topic that's not directly related to I/O, although it has a tenuous relationship to it. It's more about this notion of initializing variables. As we've discussed before, this technical term initialization means giving something a value for the first time. Now, we have seen two different ways of initializing variables so far. One is with an assignment statement, and the other is with scanf, which also changes memory. So that could be used as a way of initializing a variable. Today I'll show you another way that some programmers like to use for initializing variables. Let's focus on the left-hand side of the screen first. This represents some declarations and a couple of assignment statements as we've seen them in programs already. We declare the variables and then we initialize them by using assignments. Now, on the right-hand side, I've shown an alternate way of achieving the same effect with a little different notation. The line that begins int product is a declaration. As part of the declaration, you're allowed to specify an initial value, and you do that with equal sign and the value you want. So I can say int product equals sign 40. So this does two things sort of wrapped up in one. It says that I have a variable named product of type int, and it also says what my initial value is going to be. So at no point will the variable have a garbage or an unknown value. Okay. Same for the variable I5, which is being declared here and given an initial value at the same time. Now, a subtle difference here, to give us some practice with terminology, is in this assignment statement, I get 6, which I could certainly do. That's no longer an initialization. You see why? Because initialization means giving something a value the first time. When I say I get 6, that's not the first time. That's the second time it gets a value. So that's an assignment statement that's not an initialization. Just a little terminology review. Okay. Now another technicality that won't be terribly important in this course is that initializers are not assignment statements. They are technically and conceptually a separate feature. They're part of the declaration. This won't be a big issue in our course. However, in a language like C++, there are some cases where this is a very crucial difference and where very, very different things can happen in the initializer case of initializing as they do when you do an assignment statement. That's why it might be useful now just to be aware that this distinction exists. You will see it again if you go on to program in a language like that. Just for fun, again, since this is Friday, we're going to have a quiz. All right? Here is the quiz. I have a program, complete program. It's kind of a dumb, nonsensical program. It doesn't implement any real algorithm. It's just for a quiz. You know how teachers are. Okay, now what's the question of this quiz? Well, question at the bottom is, where is each of A, B, C, and D initialized? A, B, C, and D, you see, are variables declared up here. And so the answer should be of the form, A is initialized on such and such a line, B is initialized on such and such a line, and so forth. Okay, so you really have 4 answers to come up with for this quiz. Let's do one of them together. How about A? A is declared on line 2. Let's scan ahead. Is it defined anywhere else, or declared, or initialized, or used, or referenced? No, I don't see it mentioned anywhere else in the program. Okay, so maybe because of that you're busy writing your answer that A is initialized on line 2. It must be, because that's the only place it's mentioned. Okay, if that's what you wrote for your answer, score it -1. Line 2 is not an initialization for array. So declaration and A is still uninitialized, has a completely unknown value. So the answer to this trick question was A is never initialized in this program. Okay. Ready for B? Let's do B together, and then I'll let you do C and D at home. Okay, or with your study group. Let's see. B is declared on line 2, and it's mentioned again on line 3 and line 5. Well, let's see. The thinking you might go through is this. B is not given any value on line 2, so that can't be the answer. On lines 3 and 5, both those cases change the value of B, so they might be initialization. But there can only be one initialization, that's the first one. So the answer here is line 3. Got the idea? Okay, see what you can come up with for the other answers to this quiz. Next time, we're going to start something that's quite different from the track we've been taking so far. It's a really powerful, brand new type of statement, the conditional or if statement. I think you'll find it interesting, and I hope you'll join me then as we talk about conditional execution.